Good morning.
Okay, I can see there's a number in class. I'm not sure whether others will be coming in quickly. So this is the first time in the second semester we're introducing the course outline. I finished marking the first semester. Doesn't look bad, but I think you could do more, even though we insisted that we have to sketch all the questions that we are attempting. Some of us looks like during exams, then you forget. We agreed last time that you normally have to sketch so that we see your interpretation of the question. So that should continue this semester. So last semester was mainly the devices that enable microwaves. In this second semester, it is structured such that we are going to look at the path mainly of a transmission. Apart from just the initial devices like lasers, mesers, and parametric amplifiers and antennas, the rest will be about propagation, the paths that the waves take, or what they are confined into as they propagate from one point to another. And then more about the design of the link. What factors do you consider when you want to design a link or you want to install a communication link somewhere? The other thing that we're going to look at in terms of those links is what is the type. It could be a terrestrial link, meaning near the Earth's surface, or it could be a satellite link from Earth station to the satellite. So those are the two orientations that we have. Others would be propagation over water, flat surfaces, or Earth curvature. We'll have to look at how do those parameters influence the link design as an engineer. What do you consider while setting up a link? The other thing would be there are several layers of communication when you talk about the space. Could be that the waves are propagating on the ground surface in space, and they're affected by a lot of factors like density of trees, water vapor, oxygen concentrations. You could have rainfall attenuation. When there's rain, you would have effects depending on the frequencies at which you're transmitting. So we need to consider all those factors and see how you include them in your link design. And of course, there are regulations that are used so that you make sure that the link design that you are doing as an engineer is a standard link design. So you'll have International Telecommunication Union recommendations from, we can consider factors. So they normally have recommendations for different parameters, like if it is rain attenuation, then there's a certain recommendation for that. If it is snow attenuation, there's a recommendation for that. So our concern in Kenya would be then rain attenuation instead of snow. Cloud, because now we have a satellite link. You're transmitting through space, cloud. In the cloud itself, there are different temperatures. There are also certain times where you have sunspots. So again, there is a range of temperatures from the sun as you go towards the sun. So again, we look at what seasons do we have sunspots and how do we affect the link in terms of how much is the signal attenuated before it reaches the receiver. Apart from that, we'll be looking at last but not least, again, there are regulations about health and safety. You could be talking about International Commission on non-ionizing radiation and protection. What are the recommendations that they give? We also have CAK, Communications Authority of Kenya. How do they interpret the ICNIP standards to CAK standards for Kenya? And what are the levels of the specific absorption rates that we expect, the maximum that we expect in the environment, so that people are not affected by this increase in temperature due to non-ionizing radiation. And you know, RF, EMF normally falls within the band of non-ionizing radiation. Are they dangerous? So we have to look at RF EMF health and relate them to the standards. You can have the ICNIP standard, CAK regulation, and World Health Organization regulation. So again, using those ones, we see how we can interpret, and we have to relate it to the kind of links that we are installing and the antennas. So we have to see how does the beam width affect the SAR level, the antenna type, polarization, the transmit power, ERP, antenna type we have talked about. We could also talk about the distance from the antenna. Are you at a BTS? Are you under the antenna, or are you far from the antenna? How far are you? And what are the transmission powers from those antennas? And what frequencies are the antennas utilizing? Is it a TV station? Is it TV transmitter? Or is it for GSM? Is it a microwave oven? Or you have GSM phone? So what are the levels of the SAR? So that again we consider in the health effects. This semester again, because I can't write well, but not that's the main reason, but we are still going to use flip learning as we have used before in 5th year, where we are going to have group work. Then the group will choose team leaders who are going to teach us. So that's called flip learning. And we continue with our tutorials as usual, the CAT, and then the exam. So for the first one, we look at, I'm going to send you this if you don't have the course outline. The preliminaries we will do, where we just need to see, when we talk about a communication system, in terms of telecommunications, what do we have? So we'll give an end-to-end description of a communication system where you send a signal and then you receive it in error, and we see what amounts of error can you obtain depending on the modulation scheme that you're using. That is just to introduce you to a communication system. It's not about learning telecom. So that we'll do when we're talking about implementation of the bit error rate for binary phase shift key modulation on Octave. Octave is just like MATLAB. It's open source. So the first topic would be on lasers and mesas. Again, here we define what a laser is and the mesa, application areas and operation principle. That's all we need to do for the devices. So we need to differentiate between a laser and a mesa. What's the difference? And the parametric amplifiers. Again, for devices, we define what they are, the principles of operation and the application areas. And of course, devices normally have limitations and merits and demerits. So if you can define those ones for lasers, mesas, and parametric amplifiers, that should be done. In terms of antennas, we'll have to look at the types. Antenna types are mainly depend on the shapes. Okay, so we look at the types in terms of their shapes and how do we feed the signal into the antenna, the methods that are used for feeding signals into the antenna. So if you talk about a dipole, you need to define what that is. A dielectric rod, a Yagi antenna. So when we're saying you define, it means you should be able to sketch so that we differentiate from the shapes. Okay, so the dipole, will want to see how you sketch it. A dielectric rod, a Yagi antenna, slot, rhombic, dish, and the loop. And you can see, as we have agreed, that it depends on the shapes. So Yagi, probably you had seen them in the former local TVs, which are not the smart ones. So you'd have a Yagi which has an active dipole plus some that are directing the waves towards the active dipole. Most of the old TV or traditional TVs would have this Yagi antenna. So probably I've seen it is folded. Okay. The antenna is folded like dipoles. Then they have some I don't know what shape to give. I'm not able to draw. Let me see if I can draw. Okay. You have seen that kind of antenna. So the signal is fed into one of the dipoles here. And this, then this, we have these other ones which are meant to direct the signal towards the that dipole. So that's a Yagi. You have also seen some antennas in the BTSs that look like this. What kind of antenna do you think this is? Then you have also seen some for mainly satellite receivers. It's some rod there. So they have a reflector. There's a rod here, electric rod. So you have seen that dish antenna. The question that may come is, if this diameter here is, let's say, 60 centimeters, and you have another dish antenna whose diameter is 1 meter. Which one do you think will have a higher gain? Is G1 or G2? Okay, so those are the learning areas for this semester, right? So with a bigger dish, definitely you're able to collect more signals falling onto this, isn't it? And this dish is constructed such that it's parabolic a bit, so that all these waves that arrive here will be reflected towards the rod here. So because you're able to collect from a wider surface, then we'll be able to see that the gain is going to be higher for a wider dish. So anyway, those are the learning areas for you this semester. So we'll be drawing the antenna types, and then we discuss principle of operation and the application areas in the market. And this will depend, the discussion will be driven by certain parameters like the directive gain. So we need to define what directive gain is, directivity, and radiation intensity. Okay, so these are what make them different in terms of the principles of operation. So when you define directive gain, directivity, and radiation intensity, when you compute those factors based on the area of capture and also the beam width, like if you are to transmit a signal, how far does it go on this surface? Then, of course, as we said, how do you feed the signals to those antenna ports? So we can have an inset method, probe, coupled, aperture, quarter wave, or balloon, balanced and unbalanced method. So as we can see, like, because we are like about 40, a group of 10 is too big. But the second semester is normally easier. So it depends. So we could have like how many groups? 5 or 4? Just 4. But 10 is too big. Anyway, that you can discuss. Then when we come to radio wave propagation, we have said that the propagation could be near the ground or in the sky or space waves. So we'll also see when the waves are traveling in these different spaces, how does that affect the link length? Because you may just want to transmit from point A to B. So if you have your antenna here, It has its own height. The other one may not necessarily be on the same height. So when there's transmission happening, you form a Fresnel zone. It doesn't just go in a straight line. So there's an area here on which your signals are transmitted here. So there's a way you define that region as a Fresnel region, and you can determine the diameters at the middle, okay, or the radius. And should you, so what we will be considering is this path could have some trees, okay? So you know the location where you want to receive your signal and where you're transmitting from. But the path could be having some blockages, or let's say some. So the Fresnel zone will help you determine how far from this tree here should the center of the Fresnel zone be. Because if you make it, your path go through a tree like that, then the signal dispersion and attenuation will occur, and you may not obtain or receive sufficient threshold for your communication. So it means you have to raise this antenna height such that you avoid this. So that design problem, you will have to determine the Fresnel zone, and that will help you with determining the antenna height so that you receive sufficient threshold here for communication. Okay, so that's the design problem. So you must understand what are the effects if you are transmitting near the ground, or in the sky, on the space waves, because again, space waves have different concentrations of electrons. So you could be in E or F layer. There are different concentrations, and that affects how signals are transmitted back to the atmosphere. And also oxygen, water vapor, there's a way they resonate with certain frequencies. For example, at 60 gigahertz, the wavelength at 60 gigahertz, the millimeter wavelength there is almost the size of the oxygen molecule. So it means there's going to be a lot of absorption happening. So if that happens, it means if you transmit, for example, if you're transmitting from point A to point B at 60 gigahertz, and there's oxygen concentration there, then it means if you are to do a 15-kilometer link, and there's a lot of attenuation due to oxygen, so it means you can only do 2 kilometers. It means your link will never work if you are transmitting at 60 gigahertz. So we need to determine also what are the concentrations of oxygen, water vapor at certain levels in the atmosphere. So that's why it is important for us to study that. Water vapor also is a certain frequency where they resonate. Okay, so the ionosphere, we consider that the DEF layers. At what frequency do we have a critical frequency where these signals are reflected back, beyond which they will not be transmitted back, they will go into space. So it means if you are to transmit a signal from Ngong to Uganda, that will most likely go towards the space layer, maybe D or E layer. So at what frequency should you transmit so that it is reflected back? Okay, so those are the things that you are going to determine in the atmosphere. When we talk about the terrain effects, sometimes you plan your link through a hilly area, like Londiani area, when you're going to pass Nakuru towards Kericho. You could also be planning your link over the sea or some water. So we know that these are media for communication. So there is conductivity, okay, and permeability changes here. So those parameters change absorption or reflection of waves. So we also need to determine that. Is it a flat surface? If they're so flat, you're transmitting on a very flat area, it means there are no obstacles on the path that are going to, let's say there was a house somewhere, it's a building somewhere, there are some trees somewhere. So if you transmit through this, as much as it looks like that path has obstacles, but you realize that sometimes the reflections that you get from these obstacles end up concentrating the waves at the receiver. So sometimes you go to the field and then transmit signals same distance, and you go to another area with obstacles, then you realize the signal levels that you're receiving in a flat surface are lower because this actually disappear into the environment. But for the ones with the obstacle, they're reflected into this receiver. So sometimes the flat area is worse than a place with a hilly or, let's say, with obstacles. So again, those are learning areas that we need to see when you are doing your link design. And these are practical things that engineers do in the field. Some of you might have gone for internships there or attachment. So that's I think we have talked about Fresnel zone, the line of sight designs. Yeah, so line of sight, that's where we consider Fresnel zone because you want to only transmit where you are able to see the receiver from your transmitter. So that affects the frequencies that you want to use, the link length, and the antenna height or antenna type that you're going to use there. Or the length. You can decide to shorten the length or increase it so that maybe you take it to a hill somewhere. But again, you have to consider what is the transmission power that is required, and you must not go beyond the maximum transmission power that would cause effects of RMF, EMF radiation. So you're bound within those regulations. So that would be on radio wave propagation. It's more of the paths that are taken by the wave, okay? And how does that influence your link design? The other thing that is important that we are going to look at is communication channel models. A channel model is anyway, second semester is quite easy because you're just talking about a link. So you have of course, they are all transceivers, but let's just say you have a transmitting side and a receiving side. But they're all transceivers, they're all TRXs. So let's say that's just one way. So you're transmitting to this antenna. Let's say even your phone, this could be your phone. If you have a smart one, probably you have 4 antennas or at least 2. So we can have 2. So when you're receiving your signal from the BTS to your phone, there's path 1 and path, because you have 2 antennas inside your phone, so they receive signal differently. So we can say this path here, the channel can be described as H1 and here H2. So what you're receiving here is Y1 and here is Y2. Because there are different physical antennas in the phone, so if the antennas in the phone were communicating, 2 antennas in the phone, so you have Y1 and Y2. So because they are physical, it means at this point, when you are sampling at antenna 2 and an antenna 1, N1, the noise that you're going to obtain from antenna 1 is different from the noise that you're obtaining from antenna 2. So the communication channel will look like this. You have received Y, so let's say Y1 is equal to your signal that is transmitted, which you have already modulated within the phone, is H1. The signal is X that was transmitted after modulation. That is what we transmit, plus N1. Then Y2 is the channel 2, H2X. X is the same because it's just one signal that was transmitted, plus N2. So when we talk about a communication channel, we are looking at Dan, I've seen your yeah, sir, thanks. So sorry for that. So when we talk about the channel, we are talking about this description of this H here. How is it distributed? And then when we talk about noise, most of the time we just say the noise is N is distributed as AWGN. Additive white Gaussian noise. Additive because we are adding it, is added into the signal. So that if you had a signal like that, then with the noise, it will be something like this. Okay, it's noise, so it's additive on that. So this with the mean, so you have variance 1 and mean 0. So such a PDF is drawn like this. It's a bell-shaped PDF. This is AWGN. So the PDF, so variance 1 and mean 0. So you can have, if you have, so that we normally leave noise as additive white Gaussian noise. White, the distribution of power is the same for all frequencies. That's what it means. Gaussian, it means it is bell-shaped, right? The additive is because it's added onto the signal. So that's why we call it so. For the channel here, though, depending on the paths that we have discussed here on radio wave propagation, the PDF may take different shapes. For example, if the rains in Kisii or Kakamega are this big, the raindrops, some are small. So if the signal is coming into these raindrops, okay, in Kisii, and we say Mombasa is normally just all Russia, eh? And the signal is coming the same frequency. So the attenuation that we are going to have here is going to be different from attenuation in 2. So you may realize that the ones with the larger raindrop, the absorption takes place more. So it means when we do our distribution, we realize that it goes like that and then has a longer tail because of much absorption. So in this case, then this can be called a Raleigh PDF. So it means then in rain attenuation, we can consider H, that is a Raleigh PDF. A Raleigh PDF now is not going to have this bell shape. It's going to have that tail that is lagging there. And the distribution function is different. So that's why for every path, we need to know what is the communication channel model. The model is important because when you're doing your link planning, you have to take into account the seasonal variation of the path parameters that affect that link. For example, rain, as we say. The seasons for rain in different areas have different characteristics. So when you are doing link planning, you can see here, you need to provide for some power to be able to cover your path so that the transmission power is high enough when there is a Raleigh rainfall happening in probably Kisii. So your link power in Kisii is going to be different from that one in Mombasa. So how do you include that in your link planning? So that's why it is important to understand the communication channel models. And channel models is basically just the PDFs. Okay. So if we were to do a MATLAB or an octave code about this signal transmission, if it means there's attenuation due to H. So H is what is defined by those PDFs. But if H is equal to 1, this means the environment is just normal space with no interference. So we would say here initially there was rain. So we had H. But if it's clear air, we'll only be considering the earth curvature. So in that case, for clear air, so this is rain, H is defined by some PDF, and that period doesn't just have to be Rayleigh, it could be Weibull distribution, it could be log normal distribution, it could also be gamma distribution, which all of them is just the severity of the tail of that PDF, how severe it is. Okay, which means your signals, you are likely to receive them in error due to attenuation. Now let's say there's clear air transmission. So clear air, how would we write that? H is equal to 1. So why 1 that you're receiving in your phone right now? H is equal to 1. So it means we can just write the signal as x, y is equal to x plus n1. But you see, n1 we can't avoid because this is due to the circuitry in your phone. Then y2 is x plus n2. Otherwise, if n were to be known, if you estimate n, it means you always receive that signal without error. You'll always receive the signal without error. But that's not the case. We always receive our signals in error because of the circuitry in the gas after the antenna. So this is how now you will describe your propagation in clear air and in rain. So this you need to know and know the interpretation. So here H is equal to 1. It means there's no multiplication of that signal by any other factor. So it just comes as a wave. Okay. Until it reaches the antenna as it was transmitted. But now here, because of signal processing, what you're going to see on the oscilloscope is something like that. Because it has a WGN in it. But you see, if you have, your smartphone have at least 2 antennas for 4G, 3G, 4G, 5G, if you have. So you are receiving 2 signals. So this is more of a telecommunication side. You have received 2 signals. So how do you combine them? So that you will learn. Because this now you receive, we are only having 1 transmit antenna is single input, multiple output. So how do you combine this signal? Because you have Y1 and Y2. So combining techniques are there, which you'll learn in telecom side. So this will be single input, multiple output. So you can combine them by selecting the one with the highest power. You can choose H1 and H2, which one has higher power. So you choose one of them and then you process it. So that's selection combining. Or you could do equal gain. You sum them. Yeah? You just sum them, and because the signal that you're looking for is X. So you can just sum them and then process that signal. So you either assume that it is coming through attenuation or no attenuation in the clear air. Because here you can see, you can just check N. What you're going to check here is you can process N1 is equal to Y1, which you have received, minus X. X is one of the modulation levels that you transmit. Then N2 also you say it's Y2 minus X. So after you do this, you compute N1 and N2, then you check which one is minimum. We always assume that noise will always be small. So you check the minimum power of noise. So you will check this minimum power, the magnitude square. So if N1 is small, then you can get whichever X gives you that minimum noise. Then you will know which signal was transmitted. So that's selection combining or equal gain combining. Or you could use maximum ratio combining. You square them. Yeah, those ones you can just take notes. You will be taught in the telecom side. So those are just ways of combining multiple signals. What is important to us for micro transmission side is to understand the propagation problem, which is the H there or no H, and the noise here. So in this implementation in Octave, in that code, you can run that code and see the plots. You will see that when there is attenuation, for example, we can have that code there, what it will give you. Let's say we are testing we have the signal power or signal to noise ratio. And we are trying to determine what is the bit error rate. And let's say the modulation type that we are using is binary phase shift keying. This one just has 2 symbols, so you're only transmitting 1 bit. You could also check whether it is FOC1. These are 4 symbols, which is 2 bits. Two binary phase shift. So if you want to look at the bit error rate, let's say you start with the 1, then 0.1, 0.01, 01, 00, 1, like that. Meaning here all the bits that you send will be in error. 0.1, it means if you send 10 bits, only 1 is in error. And you have some signal to noise ratio here. Let's say 9 dB at that point. So when you plot those curves there, which you will plot, if I give you the Octave code, you will see that this curve comes like that for BPSK. For FOC1, you can also try to check for FOC1. It means you have more errors at even higher signal power. You can have 16 QAM and all the rest until 256 QAM that's used for in 5G, or just 64 QAM that is used in 4G. So you realize that then if you plot this curve, these are standards. Then now you want to determine, how do you determine that something is a standard for 4G or 5G? So you can say that any system that you have that would give you 1 out of 10,000 bits in error at 9 dB, then you say that's the standard for 4G. Okay. So when people do research, the researchers, whether you're in R&D in the industry or in a university, the desire is always to try to get this curve here to come on the left. Okay, or this one, or if you are working with BPS, to come to the left. So if you're able to make it to move to the left based on any signal processing mechanism, in that case you have achieved something. So there are standards already, then research will make them to try to come to the left. And if it comes to the left, then you move it from 4G, you take it to 5G. Okay. So we need to understand how these channels affect communication. Then also there's a Doppler effect when you are traveling from the BTS, you're moving in your car. At what speed would you have this Doppler effect where the center frequency shifts? And that's where we have, now this is called flat fading, this one here. But if it were to change in time, then it called this time selective fading, which will lead to that Doppler effect where the center frequency changes. And that now gives you a lot of problems. So there's a certain speed at which you can go in your car so that you don't experience that Doppler effect. So again, that you'll have to determine. And how do you calculate the Doppler frequency? The other one is impulsive noise in power line communication. Impulsive noise in power line communication. Let's say you want to communicate from an upstairs office to a lower office using a power line as a communication. So you have some, coupler that you connect to your laptop into the 3-pin socket for power. But remember, the channel is so random, because if you're in an American wing, somebody could be in the first floor plugging in a laptop, somebody's removing something from the lab, or plugging in a machine in the lab or somewhere else, electronic lab or computer lab. So there's a lot of, impulses coming into that power network. So again, we would want to just a little bit learn about impulsive noise in a power line communication system. So how will the impulsive noise? So each time we're talking about the channel, you have to write. So we have said here the rain. We can have another one for power line communication. Here, our signal would be, let's say Y1 is equal to H. In the power line now, it will be X plus N, which is impulsive. So when we talk about impulsive noise in a power line communication, it is X plus N, but that N is impulsive. So impulsive just means that apart from the Gaussian noise, which are random with a mean 0, you also have impulses, instances of impulses. When somebody inserts something or removes any device from the sockets which are not under your control. So it means now we'll have this Ni being a summation of the AWGN plus the impulses. So you get the PDF of AWGN, which is normal bell shape, plus the impulse in PDF. So that will give you the impulsive noise. Again, there's a way we write that. There's a class A and a class B impulsive noise in a power line communication. So if you can appreciate clear air, which is purely AWGN, in this case, we will learn through rain attenuation, which is a Rayleigh fading model, and then a power line communication, which is an impulsive noise case. Then you should be good to design any other link. Okay, so that's the knowledge areas in the communication channels. For communication channels, I think I have some dry notes you can use when you are discussing those, but you always sketch. When you come to link planning, we have a Freeze equation that relates the transmission from the transmitter and the radiation intensity at the receiver. It is called Freeze equation. A very simple model of equation, just relates both the two. When you have a transmitter and a receiver and the radiation area, the radiation intensity for the transmitter and the receiver. So it gives you the directivity of both the antennas that you have deployed, and gives you an equation that relates the power that is received at the receiver. Then you need to describe how that leads to different power when you have a different frequency or polarization. Polarization, I don't know whether we discussed it before. I think you've met it many times from third year or even before. Polarization is actually the orientation of the electric field. That's how we define it. Which means also the orientation of the magnetic field anyway, because we are talking about electromagnetic fields here. So depending on the antenna design, you could actually just have one antenna width. We have just one antenna with the two polarizations. So what would happen is that you could have a vertical. That's how the air, the space in the air, the energy is propagated in the air. Or you could have a horizontally polarized one. So this could actually just come from one panel of an antenna, both. In fact, nowadays they do, if you get those BTSs, the slot antennas there, they would have both polarizations. So it's called dual polarization. This is helpful because just within one transmission, you can actually have two signals going out, S1 and S2. And they will not interfere with each other because they have different polarizations, which you can detect at the receiver. So this gives you double capacity. And again, frequency, of course, then the wavelength. How does that then affect the power that you're receiving? And how do they relate with the interferers like raindrops? Because if this was to it's horizontal based. So it means if there was a raindrop at that point and a raindrop at that point, which is the same point in time, you see there are two instances where this signal is affected. But this vertical one, the raindrop would just be there. So you can see that this, because of that orientation in time, two signal points could be affected at the same time. And this vertical one, only one. So you can see that if we look at this, horizontal polarization would lead to more attenuation. Okay, if you're having terrestrial communication. So that's why it is important to understand polarization as well. When it comes to rain attenuation, here you'll be considering physical approach. Physical approach just means that we're looking at the raindrops. What are the sizes? So there have been campaigns on measurements of rain in different locations. So at TUR 530 here, it's a standard, will give you the distribution in certain areas on Earth, but in Africa, I think the measurements have not been well done. Though in Kenya, we got some from the military, some information. So we have the distribution of rain sizes, drop sizes around Kenya. So this what you do. So you analyze in that region. So it has to be a certain region, and then you analyze the raindrop size distribution, because that is going to affect how these waves are absorbed within the drop. If you are transmitting at very high frequencies, the wavelength is going to be very small. So it means your signal could as well be absorbed within just one big drop. So if it is absorbed, then it means you can't have it. What it does is that the absorption here, the power in that wave would try to warm this water molecule here, and then it just dissipates as heat. So you cannot no longer have that signal out. Shall have been attenuated through absorption. The smaller ones would probably scatter depending on the size of the wave. So there's a way you model the scattering. It can be Mie scattering or Rayleigh scattering. Absorption because of the larger raindrop sizes. Just the same way we are seeing the scattering in the blue sky there, okay, which is causing the blue sky. So scattering then sends back those wavelengths. But absorption would actually make it try to raise the temperature of that molecule, so you lose your signal. So here we consider this raindrop size distribution is well studied, so you can have a look at it. It leads to the number of those raindrops is what, when you count all those raindrops over time, then you have the rainfall rate, which you can say is some certain amount in millimeters per hour. For example, let's say in Kisii area, it could be 90 millimeters per hour. In Mombasa, we could say 30 millimeters per hour. So how does then, you can see now it's different, the rain rates are different. So we need to consider how do these DSDs contribute to specific attenuation, like what is the power loss in dB per kilometer? Because if we have that specific attenuation, then we can multiply over the length of the link. So L kilometers. So if we know specific attenuation, which depends on the Mie scattering and absorption, if we are able to determine that region, or if it is a standard absorption rate and scattering of these raindrop sizes, then now you can have some reduction factor on the length of the link. So that now the attenuation, full attenuation on the link is the specific one times the link length. But this link length should be the effective link length. Effective because when it rains, there are spaces into it between the raindrops. It's not just fully covered with rain. So it means we need to actually consider that if you put these raindrops together, if you have some reduction factor there, or path factor times the real link length, so that will give us the attenuation over that link. So if you can calculate this attenuation over that link, that will now tell you that whenever it rains, the power that you're going to lose is this amount. So when you are transmitting, transmit in excess of this power so that you still receive your signal within the threshold. So that's what you learn through attenuation. So that's the physical approach for the specific attenuation. Empirical approach is that you need to know this distribution. This R here would depend on the location. It's dependent on the location, the frequency, and the polarization. So it's location dependent. The rain characteristic in Mombasa is different from the one in Kisii or Kakamega. So it means this R should change. This R is defined by ITUR standard, ITUR P530. So you just need to go and look at it and then have parameters which are local to you and then change the value of that R. The other thing is just now the orientation. You have said it can be oriented as a terrestrial path, or it could be a satellite. So your link could be going to the satellite. If it is going to the satellite, then it could be rain on the path or clouds. So again, that ITUR will give you some of the parameters that you need to use. We know the height of the cloud, depending on the location again. So that will affect the distance between the antenna and the cloud, because this slant path here could have a different length depending on the location. And this cloud here also have different temperature ranges. So how does that affect? So again, that the TUR standards give you those parameters to consider. So that's where we come to terrestrial and satellite radio links. The orientation is the key thing. Okay. For the terrestrial, it's just horizontal length. For the satellite, now you can see there is a slant path, which you need to consider. Apart from that, is on the radiation, EMF health. So normally here we have EMF health and safety. So here we'll be mainly looking at the International Commission on Ionizing Radiation Protection, World Health Organization, CAK. For health and safety, they do tests in the environment, environmental assessment, and they want to see the levels of RF EMF. And here we are talking about electric fields, intensity. From there, you can actually get magnetic field intensity and power. So you just use a costimeter and walk around and determine the power in the environment or the electric field intensity in the environment based on this standard. So you look at CAK wants us to determine the occupational safety. For those engineers who work near these antennas, or within the BTS site, or the public people who are now away from those antennas. How far are they, and how are they affected when they are that far? For you, you should also learn about maybe microwave oven that we use at home or your phones. Okay? Then again, you need to understand the effect, and what we use to model that is called specific absorption rate of a microwave. So specific absorption rate just measures the power that is actually absorbed by a certain tissue. So it could be your skin, could be the bone, or you want to take which other tissue, you may want to check the brain. So we classify such that if you're looking at this, you need to look also the age set. Is it different for a child, a female, male, or an adult? And how far are you from maybe a transmitter or something like that? So that's what we discuss in EMF health and safety for RF EMF. We need to relate into those regulations because you may go to work where you're doing environmental impact assessment, and RF EMF is one of those factors. And actually, CAK also requires all the companies working with the radius to report on occupational health and safety and public health and safety based on the specific absorption rate. So it's important that we understand that this semester. When it comes to that, the guys will be discussing that. I just want to see if we can Google. We have done some field work with former students. Let me see if it's here. EMF health. UN, I think it's UN PowerNet. Now the tablet isn't responding. Not that. Just hold on. Should be unpowernet.com. Oh, I didn't write correctly. UN. Yeah, so the team that is going to look at this, I expect you to get a lot from here, because this we did a lot of work where we are doing field measurements around highways in Kenya, specific buildings, and the CBD and everywhere else in the states. So I expect that you'll get information from here. So here we are just considering RF radiation activity, whether it is 2G, 4G, 3G, Wi-Fi, anything that where we get a radio, we will do this. So you come here, you can look at the technologies that you want to study. You can look at 2G, 3G, GSM, Wi-Fi, cellular, satellite, and see how that affects them. And then you can go to and see the presentation on webinar 1. This was in June 2021. This was basically during COVID period. Papers there. Some were considering how does 3G affect, and what are the power classes within 3G that affect this SAR levels. So you can look at paper 1, paper 2, paper 3, and paper 4. Then the field measurements, you can see some of the samples there: highways, Kisii, Kisumu, Machakos, Mombasa, Nairobi, Nakuru, Nyeri, Rongo, Sarit Center. Let's see if we can access Sarit. the hub current search center. Okay. So you see somebody walked there on the first floor, the electric field, the search center. So these are just areas within the search center. You can see some were low, electric field intensity from 0 to about 8. Then in the middle there, at certain points, 92 there, you can see it goes up to 16 volts per meter. So there's a first and second floor shop section, ground floor near Safaricom shops, then CCTV cameras location up to 8. Yeah. So you can see the students did a lot of work. Of course, it shows you the location as well. So you can go there also, just sample some of them. You just need to take the URL there, emfhealth.unpowernet.com. That website, you can get all this. Let's see the highways. Yeah, you can see the highways are here. Nairobi Ahero Highway, then we can go to Londiani. I know Londiani was bad. This is after you branch off from Nakuru, you go towards Kericho, then you branch off towards Moroni, I think. So you can see Londiani area winding road, it was going up to 20,000. No, but this is millivolts. So that is 20 volts per meter or 25 volts per meter at certain area on the road. Okay. So you can see this is a problem with the winding roads in Londiani is a hilly. So it means when the transmission link is different from the distribution link that you are using when you are communicating on your phone from the BTS. So the transmission link is the dish. You will see the dish antenna. There's always a drum on the BTS that links that BTS to another BTS. So when you are planning your link on a hilly area, you may be seeing the hill that is going to receive that transmission link. But in between, there's also a hill where people live. It means that middle hill would actually experience very high levels because the transmission link now is a very high power link. So it's not what we call the air interface between your phone and the BTS. Now that is for the transmission. And you realize the Fresnel zone could be near the Earth's surface. So this is what happens. Okay, so you can have some of the. Then we also had, for example, you just wanted to see. We wanted to make this as simple as possible for anyone. It doesn't have to be an engineer to check. Let's say the microwave that you use at home. You can come here, then select. You just want to see the SAR levels, whether it's dangerous or not. So you have a microwave, the RF source. We have said it's a microwave oven, isn't it? Whom do you want to check the effect on? Is it a child or an adult? Let's say adult is the one that is normally cooking there. Could have any male cook or female. The head size now, because through CDC Cambridge, we are able to get there. The head sizes, average head sizes for adult female, adult male, infant. So this would come automatically. Then how far are you from the microwave oven? Let's say you're just going there and you're staying like, just if you are just very close to it, maybe 4 centimeters. And you want to see the effect on which tissue. Is it the skin, fat, bone, or the brain? So you could have just your skin which is exposed. What is the result here? It shows you the SAR level of 4.8 watts per kilogram. 4.8. So take note of 4.8. That was a male. 4.87. Let's now change to female and see the difference. Okay. You can see the female is now 5.13. Can somebody explain why? Why has that changed? Okay, so those are some of the things we are going to learn, and this is important. Anyway, either way, you can see that if you're only centimeters from that microwave oven, it's really dangerous because the standard says it should not go beyond 2 watts per kilogram. Here is 5. Now let's change the distance. So how far can we be? 10 centimeters away. You see how drastic it goes. 10 centimeters away now, it is 0.45. So you are safe. Right? So that's why we're talking about health and safety. More so on safety. On health, there are still discussions on how does it affect you in terms of the chemical composition in your body, blood-brain barrier in the head. Does it now cause the blood to go through into the brain, things like that. So those discussions are ongoing. If you look at the webinar there's a presentation there you can read as well and give us good notes out of that. So you can see, you can also check for, that was microwave, you can also check for a 4G phone. Okay. So a 4G phone, you want to check it on who? Adult, an infant could have it, maybe female. Okay. How infant, now you have to give us how many months? Maybe 20 months. Then next, that will help us determine the head size. How far are you from your phone? You normally put your phone on your ear, so it's 1 centimeter. So the skin in your ear, calculate. Okay, let's say 0. If you put it onto it, 1.97, not bad. Okay, so it's 1.97, which is almost 2, which is near the threshold that is dangerous, right? So you just need to move it a little bit away from your ear, and it drastically drops to 0.43. That's on the skin. If you have some fat around the skin, is too low. Bone, does it reach? No. Propagation is on the skin depth. So you can see the brain is going to be very safe. Okay. Though the permittivity and the permeability of these tissues are different. Okay. So when it's on the brain, you can see there's higher power there. But if it's on the bone, it's less. Okay. So it means the brain is permeable to these signals more than the bone. But it's still safe. Those are very safe levels. You can see, you can have your details there, computation summary, the technology is 4G, phone on the bone, impedance. Now these factors, we have them also. Intrinsic impedance, the skin depth, we can calculate. We are calculating that in the background, but for you now, you have to show us the formula for doing all this. The skin depth, the power density, the E field, and the SAR. Okay, and that is well explained on the home page. So the guys who are going to discuss this, you have, this is the skin depth, then the factors you consider, SAR definition, how does it lead to power density, and after the power density, you apply the tissue and get the SAR on that tissue. All right, so this is where we were. So that is all for this semester. It's normally easier, even the pass rate, not really pass rate, but the marks normally much higher. Everybody passes. So you just need to maximize. But what is key for a 5th year is really the practical part of it. You're now going into the industry. You need to know how you relate your theory with practice. That is what is important. So how much knowledge are you to come out with? Are you able to speak about all these topics without referring to any book? Are you able to sketch these scenarios and relate with what is happening in the industry? That is what is important, really. Because for you to reach here, you have passed. You have the ability and capability. You just need more skills and little knowledge, attitude, and you're done. So I'm going to share this. Aswani, is Aswani in class? Is it Aswani? Oh, no, not Aswani. Aswani is study. This is that lady. Safin.
Yes.
Yeah, I'm going to send you this one, the course outline. And then tomorrow, I can take you through this simulation. I should have another document which has that code. So for some of you who have time, so I'm going to send this one and then the simulation another one that has the simulation code. So if you don't have Octave or MATLAB, download Octave, or you can just use MATLAB if you have, which I'm sure probably is just a cracked version. I don't recommend you use something stolen, but Octave you can just download. It's a very simple, application. Then we go through how you simulate a communication system so that you see the bit error rates, and we see how the channel affects the amount of errors within a communication channel. So that when we now start discussing this, you already know where we are headed. From theory, what we want, what is in the standard for telecommunication standard, is actually this bit error rate. We are saying for 4G, we want 1 out of 10,000. For 5G, we want 1 out of 100,000 bit to be in error. So how do you achieve it? And yet you have propagation problems here. So we'll start with that top-down approach where we show the simulation on the telecom side. Telecom is actually guided by also ITU standard, International Telecommunication Union, but telecommunication standard. Us, in the microwave side, we are guided by ITU. ITU-R, sorry, here, ITU-R, radio communication. So this you must understand where we fall. Okay, so the standards we are going to consider on the radio propagation, or radio communication, this telecommunication, also with several standards. So everything we are doing, you have to relate to that standard and see what is the standard saying about antennas, lasers, and meshes. So in the meantime, you can discuss who is going to be in group A, B, C, and D. Aya, it's time for your questions, if any. I hope many people came to class. Just check. 34, yeah, so that's almost everyone there. Okay, so we are going to be online. I think for the next 1 month, I'll be away on some mobility. But anyway, for us, we've been online, so it's not going to be a big change for you from next week. So tomorrow we meet, we go through these simulations. So I'm going to send this just now. You can send in your attendance with your registration numbers.